Okay, so let's look at this one. Still a first order, but I want us to look at this one. We're going to solve this using the series method to solve this. But then now, if you try separation of variables here, we're just going to get that y is basically equals to e to the power of, let's say some constant c multiplied by e to the power of a half x squared. That will be the solution to that. C multiplied by e to the power half x squared, because basically what you realize is that y prime will basically be equals to the derivative of this one will just be x c, or it should be a negative, right? Minus, so that way we'll have minus xc e to the power of minus a half x squared. Then if you add this one with xy will just basically be equals to cx or xc e to the power of minus a half x squared. Notice that if you add these two, they'll basically give you 0. So we can already tell the solution to this one. But now we want to solve this one using the series method. So y equals the summation of cn x to the power of n, starting from 0 all the way to infinity. Okay, so if we look here, we only need to find y prime, and y prime basically starts from 1. We go to infinity, and then we just have cn multiplied by n to the power of x minus 1. So this is what we have. Okay, then just copy that to your differential equation right there. Then we basically have like the summation starting from 1 to infinity of cn multiplied by n to the power of x minus 1 plus x multiplied by y, and x times y, and y is just basically starting from 0 to infinity of cn multiplied by x to the power of n, and this is just basically equals to 0. Okay, let's look here. Notice that if you plug in 1, you get x0 from the first summation. Okay, we can take the x in. We can basically take the x in. Let's see, n equals 1, infinity, cn n x to the power of n minus 1 plus the summation starting at 0 to infinity of cn multiplied by x to the power of n plus 1. This will be equals to 0. Okay, so here, if you plug in, if you plug in 1 here, you basically have x to the power of 0. That means the first term contains x to the power of 0. But here, if you plug in 0, you have x to the power of 0 plus 1, which is just x to the power of 1. This one started x to the power of 0. This one started x to the power of 1. 1 and 0, which one is larger? 1. So we want both series to have the first term starting at 1. X to the power of 1, I mean. So in order to start here, in order for this one to start at x equals 1, x to the power of 1, set n minus 1 equals to 1, because you want both of them to start at 1. So that means n equals 2. So that means that here, this summation, we want the summation, this one, to start at n equals 2. So that means we remove the first term here. And when you plug in 1 here, notice something. If you plug in 1 here on the series here, you have c1 multiplied by 1 multiplied by x to the power of 0, which is just going to be c1, plus the summation starting at n equals 2 to infinite of cn n into x to the power of n minus 1, I mean, n minus 1 plus the summation starting at 0 to infinity of cn x to the power of n plus 1. Okay, now if you plug in the first term on each summation, it started x to the power of 1. Plug in 2 here, you get 2 minus 1, which is x to the power of 1, right? And if you plug in 0 here, you also have x to the power of 1. So they have both the same power of x as their initial values here. Now, what you do normally is that you equate this here to k. In the last video, I said you don't really need to think on this one. Just say k equals the upper term. And here the upper term is n plus 1. So we said k equals n plus 1. Okay, so now you have c1 plus, you transform that summation from n in terms of k. Plug in 2 here, you have 2 minus 1. And that means k started at 1. Infinity minus 1 is still infinity. Then you have c. Solve for n here, you get that n equals k plus 1. Then you have k plus 1. X to the power of k. Plus the summation starting at plug in 0 here, k starts from 1 all the way to infinity, and you have c, and this time will be k minus 1, x to the power of k. So you have something like this. So now, when you have something like this, what you want to confirm if you're correct, your k values should be the same for both series of it, which in this case it is the same. So Now you regroup the series, and you have C1 plus the summation starting at 1. Notice that you can factor by x to the k, and then you have something like that, and then here you remain with just ck plus 1, and then multiply that with just k plus 1, and then plus ck minus 1 from this summation here, because this summation you just remain at ck minus 1 with this positive right there. This will be equals to 0. So from here you said everything basically will be equals to 0 except for x to the power of k. So you only have c1 outside the summation, set it equals to 0. And this one you solve k minus 1 and k plus 1, the larger one here is just c to the ck plus 1. So you solve for that, and you just get that ck plus 1 will basically be negative into ck minus 1 over k plus 1. Where k starts at 1, k equals 1, 2, 3, and it's just going to progress like that. Okay, so c1 is 0, and ck plus 1 equals this. Okay, so now here what we want is to express, we already know c1 equals 0, right? We already know that c1 equals 0. Okay, start with k equals 1 here. So for k equals 1, for k equals 2, for k equals 3, and k equals 4. I think this should be enough to get a pattern from this. Okay, so now plug in 1 here. If you plug in 1, you have c2. So for k1, we end up with c2 equals, if you plug in 1 on this one here, you just get c naught, negative c naught over 1 plus 1, that's over 2. So c2 equals this. Plug in k equals 2, then you get c3 equals, plug in 2 here, you just have negative c1 over 3. So this is basically, since c1 is 0, this is basically 0. And k3, k equals 3, you get c4, and this one you plug in k as 3, you get negative c2 over 4, and c2 you already get that it's this one, negative c naught over 2. Plug c naught over 2 here, you just get, remember it comes with a negative, and you have a negative here, and then it will be a positive, then you have c naught over 8. Plug in k equals 4, you get c5. This will be equals to c, negative c3, right? Negative c3 over 5, which is just going to be 0. And let's try with the last one, k equals 5, and see what happens. You have c6. This will be negative c4, because 5 minus 1, that's 4. And then we have that divided by 6. And c4 is basically c naught over 8. So you just technically have negative c naught over 8 by 6. 8 by 6, or 6 by 8. Okay, so let's classify what happens here. You have every even degree of that function is going to be 0. For k2, k4, for every even k, that constant will result in 0 there. That coefficient will be 0. So c1 is 0, c3 is 0, c5 is 0. So you basically have the even powers of x. So you have the even powers of x. So that means that y equals c naught, and c1 is 0. So we skip c1, and c2 is negative c naught over 2 x squared. c3 is 0. c3 is 0. And then we basically have like c4 there, and c4 is just basically positive c naught over 8 x to the 4th minus c5 is 0, c6 is just negative c naught over 8 by 6. And 8 by 6 is basically 48. That's about 48. Is it 8 by 6, 8 by 5, 40 plus 8, 80, 48, yeah. Okay, then that series is just going to progress like that. This is c6, so it's x to the 6, and you have a positive there, and that series is just going to progress like that. So now if you can't think of a way forward, you can stop here, factor by c naught, and just stop there. Because if you continue and you get the wrong thing, then they're just basically going to mark you wrong. I basically can just factor by c naught and just stop there. Okay, so let's check what really happens here. Okay, is there a pattern? Do you see any pattern here? Let's see. Let's factor by c naught. Let's check what happens. Okay, so factoring by c naught, then we end up with y equals c naught into 1 minus a half x squared plus 1 over 8 x to the 4th minus 1 over 48 x to the 6th plus, and it just keeps on progressing like that. So let's check what really happens here. 2 corresponding with 2, 8 corresponding with 4, 6 corresponding to this one, and let's just check the pattern here. Okay, so let's look at this. Okay, pattern. Okay, let's do it like this. If you start this one at x equals 0, you have x to the power of 0, which is 1, which is fine. Divide by 1 factorial, which is just 1. And this one we expect to divide it by 2 factorial. Divide it by 1 factorial. But when we divide by 1 factorial, we're going to have over 1, right? But here we realize that we have over 2. So when we have an over 2, we can just basically group the half x squared together. A half x squared together. If we factor everything by a half x squared, what do we have? Okay, let's do this. Y equals c naught into 1 minus, group the half x squared together. So we just have a half x squared as 1. And now we want to group by a half x squared here. If you want to group by a half x squared, we have a half x squared. Notice that you have an over 4 here. Let's see. But we can square that, right? Because it's the second term. It's where n equals 2. Then we have an x4, 1 over 2 square. That's 1 over 4, so we're missing a half here. Okay, I think I just got a pattern on this one. Minus 1 over 3 factorial is 6. Then you have a 1 over 2 x squared to the power of 3 plus, this is it. It's good. Okay, then you just have this pattern right here. Like I said, identifying the pattern, you really need to think outside the box on that one. Okay, but then here's the pattern. This is what basically happens. But notice that this thing alternates. Positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, and it's just going to progress like that. So y equals c naught multiplied by the summation. Instead of having x, we have a half x squared to the n. Instead of having x to the n, we have a half x squared raised to n. And then we just have a 1 over n factorial of that. And notice that we also have like positive for the first term. Remember starting at 0. Positive for the first term and negative for the second term. This is where n equals 1 is negative, so we can have minus 1 to the power of n, something like that. Then y is basically c naught multiplied by the summation, where we go from 0 to infinity of, group the negative 1 with this term here, then you have 1 over n factorial multiplied by minus half to the power of x squared to the power of n. Because both minus 1 and this term are raised to n, so you can just group them together. And then what is this? Instead of, we remember the expansion of e to the x, but instead of having x, you have a minus half x squared. So this means that this one will just be c naught multiplied by e to the power of minus half x squared. So this is basically okay. You can just leave it here. It's fine. You don't really need to, cause if you force it, you're gonna get a wrong thing, but then they're gonna mark it wrong. But then if you stop here, it is a correct expansion of that. So yeah. Okay, so but this is the full answer of that, the final simplified solution of that. Okay, so just digest that for a while and we'll move to second order differential equation using a series method on that. Okay, thanks for watching. Don't forget to share and subscribe.